Hello students, my name is Justin, and today we will be learning physics. Now, physics from this textbook by Giancoli is going to be what is the AP Physics textbook that we're going to use. And Chapter 1 is introducing us to what is science. Chapter 1 includes these particular sections. 1.1 is going to be the nature of science. 1.2 is going to be physics and its relation to other fields. 1.3 is going to be the models, theories, and laws. 1.4 is going to be measurement and uncertainty, significant figures. 1.5 is going to be units, standards, and SI units. 1.6 is going to be converting units. 1.7 is going to be order of magnitude, rapid estimating, and 1.8 is going to be dimensional analysis. Now, because the first half of summer we did AP chemistry topics, the first chapter of typically every science class that you see in high school is going to correspond to the same topic. So what we're going to do is we're going to move on to Chapter 2, which is describing kinematics, describing motion, kinematics in one dimension. The first section in Chapter 2 is reference frames and displacement. In this section, we will define a lot of terms that will help us understand the concept of kinematics. Kinematics is defined as understanding motion, unlike dynamics, which describes how massive objects move. In order to fully comprehend motion in kinematics, we're presented a coordinate axis system. Particularly for this section, what we will do is we will use a one-dimensional coordinate system and a two-dimensional coordinate system. Now, you might understand this as a number line, which we first were introduced to in math, where we have x values ranging from -infinity to infinity, where all the integers exist one tick mark away. And we have a two-dimensional grid system, like a Cartesian coordinates, where we have x and y values located at every point. We can describe where an object or a person is located by its position. And the position, based on which coordinate system that you use, will have a different definition. For example, a person located at x equals 0 in a one-dimensional line, we would say that his position is at x equals 0. And if we were to draw someone located to the left of that person, we would say this individual, or she, is located at a position of x equals -2. Whereas a positive and negative will indicate where this person is relative to the origin of that number line of x equals 0, because a positive value means it's located on the right side of that reference, and a negative value will mean that a person is located to the left side of that reference. We use the same analogy in a two-dimensional axis, such that a positive number in the x direction is more towards the right, a negative value is more towards the left. In the y direction, a positive value is more upwards, and a negative value is more downwards. So a person located at this location would have a position of 4, 2, just like an xy coordinate of an axis. And a person located in the second quadrant at this point, we would say that they have a position of -4, 3. And depending on whether you have a one-dimensional or two-dimensional scale, we typically indicate that as x with an I subscript to indicate initial, or we can have an x with the F subscript to indicate final position. And this also works in the y direction as well. We could say y initial and we could say y final. When we wish to find how the position changes from final to initial, we call that change in position as a term called displacement. Displacement is defined as the change in position of the object. When we go back to the one-dimensional case, suppose that you have the starting position. You say your initial position is equal to 0 and your final position is equal to -2. Let's call this condition A. In condition B, we have the opposite, in which your initial condition is located at x equals -2 and your final position is located at x equals 0. We use this equation in which the displacement, which is going to be x final minus x initial, we just subtract the final position from the initial position, and we find the following. In case A, if you start at x equals 0 and then you're finally located at x equals -2, you notice that we have -2 minus 0, and that gives you a -2 value for the displacement. However, for case B, what we see is that when you do this same subtraction, we see that since the 0 comes first and you're subtracting a negative, we end up with a positive value. Now, this should be evident because a negative value indicates that you're moving to the left or in the negative x direction, as the x direction is defined positive to the right. And likewise, when you move from an initial position of -2 to a final position of 0, we have a +2. So what's quite interesting about displacement is that direction is also fairly important. This is like saying when you go to a friend's house, your friend's house is located 5 miles west or 5 miles east. The magnitude of the direction would be the 5 miles, and the direction would be the, as for the case in the two-dimensional coordinate system, let's imagine that the point located at -4, 3 was located as point C, and that of 4, 2 was located at point D. And let's suppose that we have two cases. One is moving from point C to point D, and the second case would be moving from point D to point C. It's redundant to include the initial and final position subscripts of I and F, because now we know that in this first case, we're moving from point C to point D, and it's understood that the primary point is going to be the initial, C, and the final is going to be point D. Likewise, the second example in this case is if we move in the reverse direction, in which we started with the position D and we move along to the point C. Now here we have to consider both the x and the y coordinate change. So as point C was located at -4, 3, this is going to be the initial position that we will then subtract from the coordinate of 4, 2, and we see that we've written this in terms of a vector notation. Likewise, in the second case, moving from point D to point C, we would start with the -4, 3 vector, and then we're subtracting that from the initial, which is going to be 4, 2. And when we do this vector addition or vector subtraction, we end up with the following. So we would have 8, -1 to show that from C to D, we move exactly 8 units into the x direction, and we move 1 downwards, or in the negative direction of the y. Likewise, we expect the position or the displacement in the reverse direction to just have the same values, but now they're going to be negatives of one another. So we have -8, +1. Let's look at a real-life example to really highlight the difference between displacement and distance. A standard track and field in a high school requires a student to run 4 laps in order to complete their mile. Now, in this track, we know that the starting line and the finish line are going to exist at the same point. And the question typically asks for a student who completes 1 mile around the track, what is the displacement, what is the distance that this student traveled? The distance will be equal to 1 mile. But when we look at the definition of displacement, we see that the starting point and the ending point are the same location. If we wish to find displacement delta x, which is equal to x final minus x initial, we see that because the location is the same, the displacement is actually going to be 0. The main concept here is that if you start and end at the same location, then your displacement is going to be 0, but your distance will be non-zero, assuming that you've moved around throughout that time. This is also true if we find that along a straight line, we have 3 locations. We have a home, we have a school, and we have a library, with the coordinates of each location given in miles as 0, 2, and 5. And let's suppose in this example we have person A starting from home, goes to school, then goes to the library. And in this scenario, we ask what is the distance traveled and what is the displacement? And in this case, both the answers will be 5 miles. In contrast, let's see what happens to person B, shown in blue, starting at home, then going to school, then going to the library, then coming back to school. And we ask what is the distance and what is the displacement. Now, displacement, as we can see, measures where this person is located finally in reference to their original position, and that's going to be 2 miles. It's not going to be equal to the distance because this person travels to the library, then back to school for a total of 8 miles. Sometimes the location of a particle or person will be represented as a graph in which the horizontal axis is in units of time and the vertical axis is in units of the position given x on the left as shown. In this example, for number 16 on page 41, let's ask ourselves what is the distance and what is the displacement based on this visual indicator. So let's look between t is equal to 0 and t is equal to 50 seconds. What you'll see is that typically displacement and distance is always going to be between 2 time intervals of your choosing. So between 0 and 50 seconds, we see that the position at x equals 0 is going to be equal to 0, and the position when t is equal to 50 is going to be equal to 10. So the displacement will just be the x of 50 minus the x of 0, which will be equal to 10 minus 0, which will be equal to 10 in units of meters. However, for the distance, what we see based visually is that the position is located at x equals 20 sometime between 35 and 40 seconds. I would assume 37.5 seconds. And from that position, it then moves back towards you or closer to you to a point at t equals 50 when x is equal to 10. So even though the displacement is only going to be 10 meters, we see that just like in this homeschool library example, the person moved to a location where x is going to be 20 and then moved back about 10 meters to say that the total distance in this case is going to be 30 meters.